Welcome to The Explainer. I am so incredibly excited you're here today because, well, we're diving into a literal geological detective story. We're going to unpack some groundbreaking new research that helps solve a planetary mystery that sounds, honestly, like straight-up science fiction. We're talking about how Earth's magnetic poles completely flipped in the past. And this isn't just about staring at some old rocks. It's about understanding the hidden, totally dynamic engine operating deep inside our planet.
Just picture this for a second. You wake up tomorrow, you pull out your phone to check a map, and the compass app, it's pointing south instead of north. Every single navigation system on the entire planet would be completely backward. Sounds totally impossible, right? But the wild reality is that Earth's magnetic poles actually swap places from time to time. The North Pole literally becomes the South Pole, and vice versa.
So this whole phenomenon, it's called a geomagnetic reversal. Now, scientists have actually known for decades that these reversals happen. We've got the data to prove our planet's magnetic field is the shifting, dynamic force. But the real mystery, the thing that keeps geologists up at night, is exactly how this physically occurs in real time. Like, how long does a flip actually take? And even more importantly, how do we find solid, physical proof of a magnetic flip happening out in the wild? Well, that brings us right to our investigation.
Section 1. India's Ancient Lava Highways.
All right, to solve this mystery, we've got to visit the scene of the crime. We are traveling back in time, roughly 66 million years, to a place and an event called the Deccan Traps, right in central India. This was a period of Earth's history that was just violently, unimaginably active. Just look at this number for a second. 500,000 square kilometers. That is the colossal, mind-bending scale of the Deccan Traps magmatic event. It's honestly one of the largest volcanic provinces on the entire planet. An absolutely massive volume of lava poured out over the landscape during this era, right around the time the dinosaurs went extinct, actually. But this lava didn't just magically appear on the surface out of nowhere. It had to travel from deep underground.
Take a look at this. These rocky ridges you see cutting right across the landscape, these are called dykes. Specifically, we're looking at the Pachmarhi dykes. These are basically the hardened, ancient highways that originally fed all that magma up to the surface. Millions of years ago, the ground literally cracked open, and magma just surged up through these exact fissures. When the eruptions finally died down, the leftover magma inside these cracks cooled and solidified, leaving behind these incredible, massive rocky walls.
Section 2. Earth's Rocky Tape Recorders. Okay, let's dive into this, because you might be wondering, what does ancient lava have to do with Earth's magnetic field? Well, we're shifting over to the forensic tools of our investigation now. Because these rocks aren't just dead stones, they are essentially Earth's rocky tape recorders. This process, it's called thermal remnant magnetization, is absolutely fascinating. Think of the cooling magma acting exactly like a hard drive saving data. Step 1, the magma intrudes into a rock fracture, piping hot and liquid. Step 2, floating inside that magma are these tiny magnetic mineral grains. While it's hot, these grains act like microscopic compass needles, perfectly aligning themselves with whatever Earth's magnetic field is at that exact moment. Step 3, the magma cools down and turns into solid rock. And finally, Step 4, that magnetic direction is permanently locked in place. The rock has effectively hit save on the state of the Earth's magnetic field.
So, for these specific Pachmarhi dykes, researchers found that the actual data storage units in the rocks are these high and low titanium magnetite particles, and they exist in what's called a pseudo-single domain state, which, I know sounds super technical, but it really just means they have incredibly high stability. They are literally the pristine hard drives of paleomagnetic analysis. They aren't going to easily lose or rewrite their data, even over tens of millions of years.
Section 3. The Smoking Gun Dyke.
So the researchers went out, sampled these dykes, and took them back to the lab to read the data. And most of the dykes showed a normal polarity, pointing north, exactly like today. Several others showed a reverse polarity, pointing south, and that's totally expected for this kind of analysis. But then they found something that completely stunned them. Now what's really interesting here is they expected to see what you're looking at on the left, neat, tight clusters showing a clear normal or reverse polarity. But instead, they found the absolute chaos you see on the right. This data comes from two very specific dykes, named PMD6 and PMD108. In a single rock structure, researchers found clear signatures of both normal and reverse polarities. This right here, this is our smoking gun.
I want you to seriously think about that for a second. How can one solid rock conduit possibly record north and south at the exact same time? I mean, if the magma all cooled together, it should all point in exactly the same direction.
Finding two polarities inside one dike is kind of like finding a single photograph that shows both day and night simultaneously. It totally breaks the rules of a single cooling event.
Section 4. Catching a magnetic flip. This bizarre contradiction, it forces us to completely rethink how these magma highways actually formed. And in doing so, it brings us to the ultimate revelation of our detective story. We haven't just found old rocks. We have physically caught a magnetic flip in action. Looking at this model of Dike PMD6, you can see the magma wasn't just one single giant burst that cooled all at once. Actually, it was episodic. The fracture in the Earth was used repeatedly over a super long period of time. Different layers, or flow units, were injected at totally different times. So some layers flowed in, cooled down, and locked in the older reverse polarity. Then a massive shift happened to the planet, and a later magma flow squeezed into that exact same crack, recording the brand new, normal polarity right next to the old one.
Let's walk through exactly how this builds chronologically. First, you've got the initial injection where magma fills the fracture. Second, the cooling phase, where that reverse polarity gets locked into the rock. Third, we have this massive gap in time. We're talking perhaps up to 1,000 years where the Earth's magnetic poles actually flip. And finally, step 4, reactivation. The tectonic stress shifts, the fracture basically unzips again, and a brand new pulse of magma shoots up, cooling to record the new normal polarity. This one single dike was an active plumbing system for so long that it literally outlasted a planetary magnetic reversal. Just incredible.
So, the crucial point to take away from all this is that we can pinpoint exactly when this happened. Looking at the stratigraphic column of the Deccan traps, researchers can connect these specific dikes to a very famous boundary. They give us this incredibly rare physical snapshot of the late-stage volcanism happening exactly during the boundary transition from what we call the C29R magnetic crone, which is the reversed period, to the C29N crone, the normal period. It is a perfect, undisputed geological timestamp.
So, to wrap this all up, these ancient rocky tape recorders prove beyond a doubt that magma flow isn't always just a one-and-done event. Episodic magma flows can actually survive and capture the very moments our planet's magnetic poles swap places. We literally have physical, hard drive-like evidence of this massive planetary mechanism. And knowing that the Earth beneath our feet is this dynamic, ever-changing system, I want to leave you with a provocative thought. If ancient lava conduits recorded the last great flip, what exactly is our magnetic field gearing up to do next? Thank you so much for joining me for this explainer, and for sure, keep questioning the world around you.